Okay, so on this slide, we will simplify the absorption coefficient using the long wavelength approximation, also called the electric dipole approximation. Because the optical wavelength is much larger than the atomic length scale, the optical phase changes very little across one atom. So the phase factor is approximately equal to 1. With that approximation, the interaction Hamiltonian simplifies and the matrix element becomes the equation shown here, where P sub BA represents the momentum matrix element. Substituting this equation back into the previous expression for the absorption coefficient, the square magnitude of the vector magnetic potential, A sub 0 squared, cancels out. This means that in the linear regime, the absorption coefficient is independent of optical intensity. In other words, the cancellation of A naught squared confirms this is a linear response result. The resulting absorption coefficient becomes this equation, which is one of the central results of the subsection. It tells us that the absorption coefficient depends on 4 key ingredients. First, the universal prefactor shown here. Second, the momentum matrix element, P sub BA, which measures how strongly the optical field couples the two electronic states. Third, the delta function, which enforces energy conservation and effectively selects the density of final states. Fourth, the occupation factor, FA minus FB, which determines whether absorption or stimulated emission dominates. Also, the appearance of the inner product of the unit polarization vector and the momentum matrix element is very important physically. It means that absorption depends on the polarization of the optical field. Only the component of the momentum matrix element along the electric field polarization contributes. On this slide, I would like to introduce a very useful material parameter for describing interband optical transitions in semiconductors. This parameter is called the optical matrix parameter, or more commonly, the K energy, denoted by E sub P. In the previous discussion, we derived the electron-photon interaction Hamiltonian and showed that under the usual dipole approximation, the relevant optical matrix element contains the momentum operator P hat. For optical absorption in a semiconductor, the most important transitions are often those between valence band states and conduction band states. Therefore, we write the optical transition matrix element between a valence band state Vk and a conduction band state Ck, as shown in this expression. Here, the small case e represents the elementary charge. Capital A naught is the amplitude of the vector magnetic potential. M naught is the rest mass of a free electron, and A sub E is the unit vector describing the polarization direction of the optical field. In arriving at this equation, we have assumed the usual vertical transition approximation in optical absorption. The reason is that the photon momentum is very small compared with the size of the Brillouin zone. Therefore, when an electron absorbs a photon and is excited from the valence band to the conduction band, its crystal momentum changes very little. On an E versus K band diagram, the transition is therefore drawn almost vertically. This is why the initial valence band state and the final conduction band state are both labeled by the same wave vector K. The matrix element shown here is usually denoted as P sub CV, and it is a function of the electron wave vector K. So we can write the optical matrix element as shown in this expression. This equation tells us something very important. The strength of the optical transition is controlled by the projection of the interband momentum matrix element along the polarization direction of light, which is described by A sub E. Next, we introduce a more compact way to express the optical matrix element by using the parameter E sub P. The expression for the absolute square of A sub E dot P sub CV is shown here. It is the bulk isotropic average near the gamma point. Its derivation requires the full knowledge of the K dot P theory, which is typically covered in the theory of electronic band structures in semiconductors. So it is beyond the scope of this chapter. However, we can still interpret this equation physically. The parameter EP has units of energy, usually electron volts. Moreover, we should be careful about its meaning. EP is not the photon energy. It is also not the energy of a particular electronic state. Instead, the K energy EP is a convenient way to express the strength of the interband coupling between conduction band and valence band states. So this expression is particularly useful in practical semiconductor optics because it allows us to replace the detailed microscopic momentum matrix element by a tabulated material parameter. When calculating absorption coefficients, spontaneous emission rates, or interband transition rates using Fermi's golden rule, we often need the squared optical matrix element. Instead of calculating microscopic P sub CV from the ground up every time, we can use the K energy, EP, as an experimentally or theoretically known parameter. The table at the bottom of the slide gives typical values of the K energy for several important 3-5 semiconductors. These values are all on the order of 20 to 26 electron volt. The fact that these values are relatively large tells us that interband optical coupling in these direct gap or near direct gap semiconductor materials is strong. This is one reason why 3-5 semiconductors are widely used in optoelectronic devices such as light-emitting diodes, laser diodes, photodetectors, and optical modulators. Now I want to emphasize the range of validity of this parameter. The K energy EP is mainly a band-edge interband coupling parameter. It is most meaningful near the gamma point in bulk direct bandgap semiconductors, where the conduction band edge is mainly S-like and the valence band edge is mainly P-like. If we move far away from the band edge, or if we consider strongly nanostructured systems, indirect transitions, excitonic effects, or highly anisotropic materials, then the optical matrix element may become more strongly K-dependent, and using a single constant K energy becomes a stronger approximation and is less accurate. So the main message of this slide is this. The optical transition rate is governed by the momentum matrix element between valence band and conduction band states. Near the band edge of many important direct bandgap semiconductors, this matrix element can be represented compactly by the optical matrix parameter or the K energy, EP. This allows us to write the squared optical matrix element in a simple material-dependent form, which will be very useful when we apply Fermi's golden rule to calculate optical absorption and emission rates.